calibrated airspeed at which a large aircraft in the EASA category CS-25 stalls. You also learned that stalling is caused by exceeding the critical angle of attack. Stalling has nothing to do with the speed of the aircraft. The critical angle of attack can be exceeded at any speed. It is worth noting here that to do so in the upper end of an aircraft's speed range is likely to exceed its structural limitation, or G limit. However, it has been shown that if an aircraft is flown straight and level, and the speed reduced at a rate of not more than 1 knot per second, then it is possible to identify the CAS at which it stalls, which will be a 1G stalling speed. This reference stall speed is the speed on which are based the recommended takeoff, maneuver, approach and landing speeds, which will give an adequate safety margin above the stall during normal operations. These are calculated as proportions of VSR: 1.05, 1.1, 1.2, 1.3 VSR, etc. There are several factors that can affect the value of VSR. They are weight, maneuvering the aircraft, increasing the load factor, configuration changes, affecting maximum lift coefficient and pitching moment, engine thrust or propeller slipstream, Mach number, wing contamination, and heavy rain. We shall now examine how these changes work. In straight and level flight, the weight of the aircraft is balanced by the lift. So the load factor, which is lift over weight, is 1. Whilst N in brackets is the correct symbol for load factor, the relationship between lift and weight has for years been popularly known as G. 1G corresponds to the force normally acting on us, that is, gravity. If more lift is generated than weight, the load factor will be greater than 1. The force acting on the aircraft and everything in it, including of course the pilot, will be more than normal gravity. If lift equals weight, the load factor will be 1, as you have seen. And from the lift formula, lift equals half rho v squared times CL times S, it can be seen that lift will change whenever any of the other factors in the formula change. Taking density, rho, and wing area, S, to be constant for this example, consider what would happen if thrust is reduced. The speed, v, would reduce because of drag. And from the formula, you can see that lift would decrease. So, to keep lift constant and maintain 1G flight at a reduced speed, CL must be increased by flying at a higher angle of attack. Any further reduction in speed would need a further rise in angle of attack, with each succeeding lower CAS corresponding to a greater angle of attack. Eventually, at a certain CAS, the wing reaches its critical angle and CL max, beyond which any further rise in angle of attack will precipitate a stall. We can transpose and adapt the lift formula to give us a formula for a 1G stalling speed, which equals the square root of lift over half rho times CL max times S. Note that density altitude does not affect indicated stall speed. At CL max for 1G flight, a change in weight requires a change in lift, and it can be seen from the 1G stall speed formula that, for instance, an increase in weight, and therefore lift, will increase VS 1G. The relationship between basic stalling speeds at two different weights can be obtained from the following formula. the new speed equals the old speed multiplied by the square root of the new weight as a proportion of the old weight, or the square root of new over old. The angle of attack at which the stall occurs will not be affected by the weight. This is provided that the appropriate value of CLmax is not affected by speed, which will only happen at speeds above Mach 0.4. To maintain a given angle of attack, say critical angle or alpha CLmax, in level flight, if the weight and therefore the lift required is changed, it is necessary to change the dynamic pressure. In other words, the CAS. For example, if an aircraft stalls at 150 knots at a weight of 588,600 newtons, what is the 1G stalling speed at 470,880 newtons? Using the formula, the new to old weight proportion is 470,880 over 588,600, which is 0.8. The square root of this is 0.894, which multiplied by 150 is 134. So the new stalling speed is 134 knots. A useful rule of thumb that can be derived from such calculations is that halving the percentage change in weight, either up or down, will give the approximate percentage change in stalling speed. In the example, a 20% weight reduction gives about a 10% speed reduction. This rule of thumb can be very useful, not least as a gross error check during exams. As you know, in straight and level flight, lift balances weight. But in a level turn, for example at 45 degrees, as shown here, the weight will still be acting vertically downwards, and the wings need to produce a vertical lift vector to balance it. However, as you can see from the diagram, the lift vector is tilted at 45 degrees, and if it is resolved into vertical and horizontal vectors, it is insufficient to balance the weight. The lift must therefore be increased, so that its vertical component balances the weight, and the relationship between the vertical force and the lift required can be found using trigonometry, using the symbol phi as the bank angle and taking the vertical force required as 1, the adjacent, lift being the hypotenuse. Cosine equals adjacent over hypotenuse, and if we transpose this formula, we arrive at L equals 1 over cos phi. Cos phi in this case, at 45 degrees, is 0.707. 1 divided by 0.707 is 1.41. So, for a level 45-degree bank turn, the lift must be 1.41 times that of straight flight, or, to put it another way, increased by 41%. You learned in the previous part of this lesson on stalling that to bank an aircraft and maintain level flight, lift must be greater than weight. The additional lift required is gained by increasing the angle of attack. The measure of the relationship between lift and weight is known as the load factor. Increasing lift in a turn increases the load factor. So as bank angle increases, load factor increases. In straight and level flight at CLmax, it would be impossible to turn and maintain altitude, as trying to increase lift would stall the aircraft. If a turn were to be started at a speed above the stalling speed, then at a certain angle of bank, CL would reach its maximum, and the aircraft would stall at a speed higher than the 1g stalling speed. The increase of lift in a level turn is a function of the bank angle. Using the following formula, it is possible to calculate stalling speed as a function of bank angle or load factor. The turning stall speed will equal the 1g stall speed multiplied by the square root of 1 over the cosine of the bank angle. As an example, if the 1g stalling speed is 150 knots, what would be the stalling speed at 45 degrees of bank? The working on the screen shows the result to be 178 knots CAS. Using the same sequence for 60 degrees of bank, a 2g turn in level flight gives a stalling speed of 212 knots CAS, which is 41% greater than the 1g stalling speed. The 45 degree stalling speed is 19% higher, and since these figures are ratios, they will hold good for any aircraft. As bank angle is increased, the stalling speed will rise exponentially. Whilst operating at high CLs, particularly during takeoff and landing, only moderate angles of bank should be used when manoeuvring the aircraft. For modern high-speed jet transports, the maximum bank that should be used is 30 degrees, except in an emergency. The normal maximum under Instrument Flight Rules, IFR, is 25 degrees, or the angle of bank for a rate 1 turn, 3 degrees per second, if this is less. At higher altitudes, the normal maximum would be about 10 to 15 degrees. In brief, load factor does not affect the stalling angle of attack, but the stalling speed increases in proportion with the square root of the load factor, in the same way as it does with a weight increase, since g is an effective increase in weight. Modern high-speed jet transport aircraft have swept wings with relatively low thickness chord ratios. For example, the Airbus A310 has a ratio of 12%. The overall value of CLmax for these wings is fairly low, and the clean stalling speed therefore correspondingly high. To reduce the takeoff and landing speeds and distances, various high-lift devices are used, increasing the value of CLmax. In addition to lowering the stalling speed, these devices, which principally comprise leading edge flaps and slats and trailing edge flaps, will usually alter the stall characteristics. From the 1g stall formula, it can be seen that an increase in CLmax will reduce the stalling speed. It is possible, with modern high-lift devices, to increase the CLmax by up to 100%. High-lift devices, which are fully described in the next set of lessons, decrease stall speeds and so minimum flight speed, enabling shorter takeoff and landing runs. This is their primary, and for airliners, their sole purpose. The EASA regulation 25.103b states that VCLmax is to be determined with the CG position that results in the highest value of reference stall speed. If the CG is in front of the centre of pressure, the CP, giving a nose-down pitching moment, as is usual, the tailplane must provide a download to maintain equilibrium, but the wing must produce more lift to balance the increased force of weight plus tail downforce. If the CG is further forward, it will produce a greater pitching moment, which must be balanced by a greater downforce from the tailplane. This in turn requires more lift to counter the downforce. From the 1g stall formula, you can see that greater lift gives a higher stalling speed, with the conclusion that forward movement of the CG increases the stalling speed. With landing gear up, the thrust-drag couple is not great, but when the gear is lowered, the profile drag below the CG is increased, which gives a nose-down pitching moment. This must be balanced by increasing the downforce of the tailplane, which in turn needs more lift to balance it. Any change of CG caused by a change in longitudinal position of the gear as it extends will have very little effect. The change in profile drag is far more significant, and the conclusion is that lowering the landing gear increases stall speed. Regarding engine thrust, the EASA Regulation 25.103b states that VCL max is to be determined with zero thrust at stall speed, and it is assumed that the aircraft is supported entirely by lift. If thrust is applied close to the stall, the nose-high attitude will produce a vertical component of thrust, which helps to support the weight, and less lift is required. Propellers will create an extra effect because of the slipstream. The most important factors in this situation are engine type, propeller or jet, thrust-to-weight ratio, and the inclination of the thrust vector at CL max. With propeller-driven aircraft, the slipstream velocity behind the propellers is greater than the free stream flow, depending on the thrust. Thus, at low IAS and high power, the dynamic pressure within the slipstream is higher than that outside it, and generates more lift than at zero thrust. The lift at any given IAS or angle of attack will be significantly affected. For instance, if the aircraft is in the landing flare and power is reduced suddenly, the resulting loss of lift could cause a heavy landing. On the other hand, a potentially heavy landing can be prevented with a judicious burst of power. A typical jet aircraft does not experience the induced flow velocities of prop-driven aircraft, the only significant factor being the vertical component of thrust. This means that, since less lift is required to support the aircraft, there is lift in hand to decelerate to a lower speed. The effect on stall speed at high thrust can be large, but since there is no induced flow, the angle of attack at the stall will be very similar to that of a power-off stall. The conclusion for both categories of aircraft is that power-on stall speed is less than power-off. As an aircraft flies faster, the streamline pattern around the wings begins to change. Above about Mach 0.4, 4/10 of the speed of sound, the phenomenon of compressibility becomes significant. Mach 0.4 equates to around 300 miles per hour. Pressure waves generated by the wing's passage through the air propagate ahead of it at the speed of sound, and cause the air ahead of the wing to curve upward, or upwash, towards the low-pressure upper surface. At low speeds, the streamline pattern is affected well ahead of the wing, and the air has a fair distance in which to upwash. As speed increases, the wing gets closer to its leading pressure wave, and the air has less space in which to upwash, and so approaches the wing more steeply. The change in streamline pattern accentuates the adverse pressure gradient near the leading edge, and flow separation occurs at a lower angle of attack. Above Mach 0.4, CL max decreases, as shown in the diagram on screen. According to the 1G stall formula, a drop in CL max will increase the stalling speed. At a constant EAS, TAS will increase. Also, outside air temperature, or OAT, drops with increasing altitude, causing the local speed of sound to decrease. Mach number is proportional to TAS and inversely proportional to the local speed of sound, or A. As an equation, m equals TAS over A. At a constant EAS, Mach number will increase with altitude. The graph, now on the screen, shows the variation of stalling speed with altitude at a constant load factor. This type of curve is called the stalling boundary for the given load factor, in which altitude is plotted against EAS. At the load factor shown, 1g, the aircraft cannot fly to the left of this boundary. You can see that at lower altitudes, stall speed does not vary. This is because the Mach number at the stall is less than 0.4, too low for compressibility to have any effect. By about 30,000 feet, the Mach number has risen to the extent the compressibility is significant and the rise in stalling speed is apparent. The conclusion here, then, is that stall speed will initially stay constant with altitude, but will increase with compressibility above about Mach 0.4. The various factors affecting stalling speed considered so far have been pretty much known quantities, explored during flight testing and promulgated in aircraft manuals. But contamination on the wing, particularly ice, frost or snow, can drastically affect the wing profile and affect the nature of the boundary layer, giving unknown and untested stalling speeds and characteristics. Let's consider the effects of these three main types of contamination, starting with ice. Ice formation on the wing will produce large changes in wing contour, particularly on the leading edge, leading to severe local adverse pressure gradients. High surface friction will considerably reduce boundary layer kinetic energy. These hazards cause a large drop in CLmax and can increase the stall speed by up to 30% without any change in angle of attack. The extra weight of the ice will also increase the stalling speed, but the reduction of CLmax is by far the greater effect. The effect of frost is more subtle. An accumulation of a hard layer of frost on the wing upper surface gives a texture of considerable roughness. Tests have shown that leading edge and upper surface contamination, with a thickness and roughness comparable to coarse sandpaper, can reduce lift by as much as 30%, increase stalling speed by 10 to 15%, and increase drag by 40%. Whilst the basic shape and aerodynamic contour of the wing are unchanged, the increase in skin friction reduces the kinetic energy of the boundary layer, and separation will occur at a smaller angle of attack and at lower CLs than a clean wing. The effect of snow can be similar to frost in that it will increase surface roughness. In addition, any deposit more than a light dusting can add significant weight and alter the aerodynamic profile. If there is any snow on the aircraft, it must be removed before flight. The idea that snow will blow off the wings during taxi or takeoff is a complete misconception, as has been tragically proved on occasions. Notably, the crash of a Boeing 737 into the Potomac River, Washington, in January 1982, which killed 78 people, and in which snow on the wings and tailplane was one of several contributory factors. The pilot in command is legally required to ensure that his aeroplane is aerodynamically clean at takeoff. It is vitally important that the time limitations, the holdover time, on any de-icing or anti-icing process are adhered to. If this time is exceeded before takeoff, the aircraft must be de-iced again. Guidance is available to pilots in the CAA's Aeronautical Information Circular number 106 of 2004, Pink 74, issued 11th of November 2004, entitled Frost, Snow and Ice on Aircraft. AICs are reissued from time to time, so you should check for updates. To summarize the effects of contamination, we can say that while the reduction in CL max with frost is not usually as much as with ice formation, its effect is probably more than may be expected from the comparatively smaller change in profile. The effect on the boundary layer's kinetic energy is a major factor influencing the separation of the airflow. The increase in stalling speed due to ice formation is difficult to quantify, as accretion rates and patterns and ice types vary greatly. Frost is a significant hazard, but will not form on upper surfaces in flight, although it does form under fuel tanks in a descent from a sub-zero high level into warmer, moist air, but this is usually of short duration. Snow, particularly wet snow, at temperatures not far below zero, presents a very serious hazard. All will affect stalling speed. The moral is that any contamination is too much, and none must be allowed to remain on any surface before flight. De-icing is essential. As mentioned earlier, there have been cases involving loss of control in icing conditions due to unexpected stalling at speeds considerably higher than the normal stalling speeds, possibly accompanied by sudden rolling. Control can be lost as a result of a contamination-induced stall, the onset of which can be so insidious as to be difficult to detect until it is too late. The following advice may help you to recognize and avoid these gradual stalls, or recover from one if it does occur. First, a loss of performance in icing conditions may indicate a serious ice buildup, possibly unseen, which is causing a gradual loss of lift and increase in drag. Such a buildup can cause the aircraft to stall at about 30% above normal stall speeds. The longitudinal characteristics of an icing-induced stall may be so unobtrusive that the pilot is unaware that it has occurred. A stall warning system, normally triggered by angle of attack, may not be activated by a low alpha stall, but Buffet may assist in stall recognition. The first clue may be a roll control problem, manifested either as a divergent roll oscillation or a wing drop. A combination of roll oscillation and onset of high drag can cause the aeroplane to enter a high rate of descent unless prompt recovery action is taken. If a roll control problem develops in icing conditions, the pilot should suspect an icing-induced stall and take immediate recovery action. The anti-icing system, if fitted, should have been on prior to entering icing conditions, in accordance with operating procedures. If not, it must be activated immediately, and consideration given to leaving icing conditions by track or level adjustment. The tailplane is an aerofoil, and because it is thinner than the wing, will tend to accumulate ice sooner and more quickly than the wing, but with similar effects. However, the tailplane, often an inverted aerofoil, usually produces a downforce. So if it stalls, the loss of downforce will cause a pitch down, with at least a temporary loss of control. Stalling of an ice-contaminated tailplane could be precipitated by the lowering of the flaps, which increases the downwash over the tailplane and consequently alters its effective angle of attack and takes it beyond the critical angle in a negative sense. It should be borne in mind that the tailplane will usually be producing downforce, which is lost if the tailplane stalls. In the event of a sudden pitch down when lowering flaps, the initial recovery action is to retract the flaps, reducing the downwash. Heavy rain, whilst not as hazardous as its freezing cousins, ice, frost and snow, can also have a detrimental effect on stalling speeds and drag. The rain will form a film on the aircraft's surface, increasing the weight, and therefore the stalling speed slightly. As the film of water runs back over the wing, it will distort the profile, roughen the surface, and distort the airflow over the whole aircraft. CLmax will decrease, increasing the stalling speed. The surface film will increase interference, profile, and form drag. The approximate overall increments are: for light rain, 5%, moderate rain, 20%, and for heavy rain, up to 30%. This extra drag increases the thrust required. A further consideration, which does not in itself affect stalling speed, is the impact of heavy rain. Lost momentum will require more thrust to maintain speed, and the rainfall will tend to push the aircraft downwards, in much the same way as microburst wind shear, with which it may well be associated. With the conventional layout of the rear-mounted tailplane, the wing stalls first, and longitudinal stability and control are maintained. On the tail-first canard layout, if the wing, the main plane, stalls before the foreplane, then stability will be lost. But if the foreplane stalls first, then control will be lost, and the maximum value of CL is reduced, since both foreplane and main plane are lifting surfaces. In the next lesson in this series on stalling, we return to conventional aircraft and the topic of spinning.